All right, cool, wonderful. All right, hey everyone, this is that programming guy. I'm back. I'm back. I'm back. I'm back. I'm back. It's getting really hot in here. So what was going on was that I had my bitrate set to 2500, which is actually faster than my upload speed in general. So I turned it down to 2K and it made life so much more easier. So right now I'm using my laptop to get back onto chat in case, you know, somebody does actually want to chat with me while I start to boy. While I start to sweat. Because it's hot in here. Create a dashboard. Alright, now I'm here and OBS should still be going fine. Yeah, alright. So that's what it was. Alright, so what I was doing was now I need to figure out, so I have the addressing mode, right? I have the addressing mode object. Right, so I have AN and DN, then address, register, index. So probably this will just be E, and then A, and then N, like that. And that's actually what would go in. So this should be the string. So basically what I see on the string should be the string for the address redirect. So really is basically what I see here is what I'm looking for. And so the register number XXXW and XXXL. What is XXXW and X apps? I think absolute addressing with 16-bit and 32-bit addresses. I think that's what it is. This is the immediate. I think we're good. So the addressing mode will be the string. So a dictionary or just a list, and then just, yeah, we can do that right now. Because, I mean, what I'd want to do is a dictionary, so I have fast lookup. But, dictionary of, addressing modes is a dictionary of, effective addressing. There we go. Reg number 01. Sure, I guess. Let's do that. Let's try that, shall we? Let's try it. So addressing mode is a dictionary. Oh my god, what am I doing? Public. Might have to get some coffee. Public class. And then from here we have effective address. Effective address. Private string mode, private string register. There we go. There we go. All right. Oh god, I guess I could use this getters and setters, huh? I don't like a class that just has getters and setters. This isn't cool. I don't like it. Alright. Within the addressing mode, DM string and Oh, no. What am I doing? Addressing modes. Yeah, this would be addressing modes. And this would be an address, not addresses. ADRESS. Yeah, address. Addressing modes. Private DIC tile and RY. String to effective address. There we go. Now we add them. So the one we want to add right now is the first one. So this really would be D0 through D7, huh? All right. Make the effective address. Oh, right. All right, yeah. There we go. So let that go in. New effective address, which is 0, 0, 0. That's it. Do the little d. So we can do both. Actually, no, just do the little d. Just do the little d. Just do the little d. Alright, just do the little d. There we go. So now we have that. Then we have AN. 001. I see. Okay, and then we have that. So really, so the idea is that I'm going toward is I would use the effective addressing mode, and I'd read it straight from the text file, and then from there I would just go straight into the addressing modes and get what I need. However, something else I could do is be like, all right, if you start with D, that's it. If you start with A, if you start with that A, do this. If you have that A and then plus, like that. So the what's the word I'm looking for? Regex might be what I need. So it's like if you start with a negative A like this, you have this. If you start with the D16AN, which I have no idea how to do that, or D8AN, so it's probably a 16-bit D and an 8-byte D. I don't know, and an XN. I have no idea. What are these? Address register indirect with displacement, and address register indirect with indexing and displacement. Oh boy, okay, this is gonna be fun. Because I was thinking something like, if I see in the file D0, then D0 would go straight to the thing, but the dictionary, but it's like if you just start with a D or a D, then I already know what you're doing. You don't have to do anything else. Or I could use a try. That's a good idea too. With the dictionary, that might be an idea too. Here's the thing, because if I do this, then there's just a contains. Or what I could do is I could include my own logic, right? I could include my own logic. And I could go if string 0 equals D, then I know it's a direct address. If 0 starts with A, it's a direct address. If it starts with maybe like I think a pound, if 0 equals pound, then it's a immediate value or a literal. Then it's like, all right, if you start with that, so basically it's like if 0 equals that and 1 equals A. So basically I could do something like that. I could do a big thing like that, but that's a lot of work. And then that's a lot of if and else's. So I might just do it the long way right now and just do it this way, which is absolutely fine. I'll just do it the long way. So I know how to get up to these. I know how to do all these. So I'm going to start with these. I'm going to put them in. So we have A and D, right? And then we have this one, which is AN plus and minus AN. So we have A, no. AN plus, which is, whoa, wait. What's the difference between this and this? Oh, parentheses AN is different? Oh, address register indirect. Okay, so let's do address register indirect first. So address register indirect is 0, 1 is 0. And then we have this one, which is 0, 1, 1. And then we have this, which is negative AN, which is 1, 0, 0. Cool. Now we have D16AN, D8AN, XN, which is like, what the hell? Which is address to redirect. So I get this. Address So now I guess I have to read up on all these addressing modes, huh? Effective addressing modes. Besides the operation code which specifies the function to be performed, an instruction defines the location on. Alright, still at 0%. A register field within an instruction can specify the register to be used. Besides the operation code which specifies the function to be performed, an instruction defines the location of every operand in the function. Instructions specify an operand location in one of three ways. A register field within an instruction can specify the register to be used. An instruction's effective address field can contain addressing mode information, or the instruction's definition can imply the use of a specific register. Other fields within the instruction specify whether the register selected is an address or data register and how the register is to be used. Section 1 introduction contains detailed register descriptions. An instruction's addressing mode specifies the value of an operand, a register that contains the operand, or how to derive the effective address of an operand in memory. Each addressing mode has an assembler syntax. Some instructions imply the addressing mode for an operand. These instructions include the appropriate fields for operands that use only one addressing mode. Data register direct. In the data register direct mode, the effective addressing field specifies the data register containing the operand. So we have DN, EA000, EA register field, which is reg0, number of extension word 0. Addressing direct mode. In the address register direct mode, the effective address field specifies the address register containing the operand. Which makes sense so far. Address register indirect. In the address register indirect mode, the operand is in memory. The effective address field specifies the address register containing the address of the operand in memory. So AN equals address register indirect. In the address register indirect mode, the operand is in memory. I see. Operand is in memory. The effective address field specifies the address register containing the address of the operand in memory. So basically, it is the address register to So it is a pointer. Basically, yes. So AN this is a pointer, which points to operand. In address register direct mode, the effective address field specifies the address register containing the operand. So basically, AN equals address register containing the operand. Alright, so address. So now we have the address register indirect with post increment mode. In the address register indirect with post increment mode, the operand is in memory. Operand in memory. The effective address field specifies the address register containing the address of the operand in memory. So it's a pointer. After the operand address is used, is incremented by 1, 2 or 4, depending on the operand, byte, word, or long word. Okay, I get it. So basically, so it's AN plus. So basically, the address register operand pointer to memory? What the fuck? An address register, the operand is memory, so yeah. Operand is in memory. The effective addressing field specifies the address register, so basically AN points to operand in memory. Yeah, just the operand memory. After the operand address is used, it is incremented by 1, 2, or 4, depending on the size of the operand, byte, word, or long. Coprocessors may support incrementing for any operand size up to 255 bytes. If the address register is the stack pointer and the operand size is the byte, the address is incremented by 2 to keep the stack pointer aligned to a word boundary. So we get the address register, which is a pointer. We add 1, 2, or 4 to the size. So we take the address register, we add that, which then points to the operand. Okay, so that sounds right. So basically, we do it then. Get AN, increment AN by 1, 2, or 4, depending on operand size. Which is a byte, a word, or long. Then use result to point to operand. All right. So I'm assuming the other one then. The other one then is the other one then gets the address register, decrements it, and then uses that as a pointer. That's my guess. In the address register indirect with pre-decrement modes, we have negative AN. The operand is memory. The effective address field specifies the address register containing the address of the operand in memory. Before the operand address is used, it is decremented by 1, 2, or 4. Oh, right, and then there's the if stack pointer and operand size is by byte, it's by 2. Then basically, if stack pointer and operand is equal to 2, is byte increase by 2, not 1. Same thing with this. If the address registers the stack pointer and the operand size is a byte, the address is decremented by 2 to keep the stack pointer aligned to the word boundary. Yes. So now we have address register indirect with displacement mode. Address register indirect with displacement. So many modes, guys. I don't know what to do. In the address register index with the displacement mode, the operand is the memory. The sum of the addresses of the address in the address register, which the effective address specified, plus the sign extended 16-bit displacement integer in the extension word is the operand's address in memory. Displacements are always sign extended to 32 bits prior to being used in effective address calculations. Okay. So basically this is, oh, it has it right there. EA equals AN plus D60. So it's basically, yeah, we have, so it's the address register. We add it a 16-bit displacement integer. All right. That's cool. So yeah. We have the address register indirect with index 8-bit displacement mode, which is 8 and then sign extended. What the fuck? The addressing mode requires one extension word that contains an index register indicator and an 8-bit displacement. The index register indicator includes size and scale information. In this mode, the operand is in memory. The operand's address is the sum of the address register's contents, the sign extended displacement value in the extension's word's low order 8 bits, in the index register's sign extended content, possibly scaled. The user must specify the address register, the displacement, and the index register in this mode. Okay, so again, we have EA equals AN plus XN plus an 8-bit thing. So just we take the contents, we add to it the integer and the sign index, and then we have the index register and multiply that by a scale value. And then we add that to get the operand pointer. Okay. So it's D8 AN XN tot and then size multiplied by scale. Interesting. So just based, all of this is almost like adding things. Okay. Address to this is what, 8-bit displacement? Base displacement. Oh my god, there's so much here. The addressing mode requires an index register indicator and an optional 16 or 32-bit sign extended base displacement. The index register indicator includes size and scaling information. The operand is in memory. The operand's address is the sum of the contents of the address register, the base displacement, and the scaled contents of the sign extended index register. In this mode, the address register, the index register, and the displacement are all optional. The effective address is 0 if there is no specification. This mode provides a data register indirect address when there is no specific address register, and the index register is a data register. Okay. So you have the base, the address, XN. So we take the address register, add it to the base displacement, and then we take the index register, multiply that by the scale, and we add that to this. Okay, number of extension words, 1, 2, or 3. Okay. Memory indirect post-index mode. This is getting fucking confusing. In this mode, both the operand and its address are in memory. The processor calculates an intermediate indirect memory address using a base address register and a base displacement. The processor accesses a long word at this address and adds the index. Okay, this is a lot of stuff that I'm not going to worry about. I just have to write it down, that's it. So, we have a lot. We have a lot. So if you go all the way back up, right? all the way back up. We have DN, AN, that, that. We have this, which is a D16. This is going to be an integer, okay. And we have this, which is D8, which is an 8-bit integer. And then there's a displacement. So really, XN is an index register. What is an index register? Here's the data address. There's no index register, is there? Instruction format field definitions. Extension. The index register type. Oh, is the direct... Okay. So, now the question is, how do I add all this, right? How do I add all this? So D, just an integer, and then integer AN and XI, oopsies, which is the, that, which is 16-bit integer. Yeah, okay, I get that. And then you have this, and so it's like the only addressing thing I can do, because D could be anything, right? So this is just an integer, INTEGER. We have an AN, which can be basically 0 through 7. We have the index register, and then we have the size multiplied this scale. So this is really interesting, because now I can't really string compare on this, because the integer can be whatever it is. The index register can also be whatever it is. So now we're in the problem is, how do we add this, right? We might just have to do a start, but I try. It might be what I'm looking for. To be like, it's really interesting. I haven't had to use a try since I was in college when I, was graded on nothing. Yay, college, man. College is fun, Alright, so, how do I store the addressing modes in a way that the dictionary can access them? Because I could do a contains, but contains is slower than equals, and a dictionary is going to hash everything anyway. This is a really interesting problem we've encountered here, haven't we, guys? Because we have EA. Huh. This is really interesting. Not really hungry. I might need some coffee. And it's also really hot in here, by the way. Like, since I turned off the fan so I could record, it's really hot in here. There we go. Yeah, so we have this, right? This wonderful mumbo jumbo. So it's like, how exactly do I match on this now? Said there's regex. However, there is a split on the commas. So there's a split on the commas. There is there's a split on the commas. Because that's a syntax that's in there. So if we go back up, that's a syntax. Syntax is DN, syntax is AN, syntax is, that AN. Of course, I can make up whatever I want to since I'm writing the assembler anyway, so I can make something up as well if I wanted to. Which is a thing, because I could make it up myself. Which I wasn't thinking about. So this would be integer and AN. Because if I was writing it, right, I would have a, 16-bit integer. So, 32, 16 bits. Yeah, 32 is in 16 bits. And then A of 0 through 7, like that. I would have that. So if the assembler gets this, it would know that it would have to take this and add 32 to it, and it would get where it needs to go, right? That's the idea. But if I need to include the addressing modes that it can use, because I'm thinking of two different problems here. I think I'm thinking of two different problems. You have one is how to store effective addresses. And we have a second problem of how to interpret effective addresses in assembler. Because I could have something like add byte D0, and then I could have something like 32A1, right? So this would be the source, and this would be the destination. How would I store the source and destination? I could store them as strings, and then, because the idea is I just want to take what I've written, put it straight into a textual format. So I can go to the dictionary and I can go, okay, this is the address register in direct with displacement mode. Right, I could do that. But then it's like, how do I store this number? Because I need to keep it. So I could be like, if start with that, separate noun, comma. Separate on comma, and then from there I could do a if 2, then we know what it is, and we can do if 3. We also kind of know what that is because we have the D8 and A, and then we have 3, so this is 0, 1, 2, so that's 3 right there. 1, 2, 3 right there. 1, 2, 3, 4. 1, 2. This is 2. And in this is this. Which is not cool. Program counter indirect. There's a lot of stuff here. So the question is, yeah, how do I'm storing the effective addressing, right? And then how to basically take that information and turn it into bytes, turn into bits, right? Because if I have dn, assembler syntax is dn, then that would be 0, 0. I don't know exactly how to store that in bits and how to write it down at the moment. Quite interesting. I'd have to check with each specific syntax. Because really what I want to go is, okay, if it's add, if it's add, then you have access to these effective addressing modes. If it's add and the destination is effective addressing modes, you can use everything. If it's add and the source is the effective address, then you have access to these addressing modes, which would make life easier. I could literally do that. I could do that. I'm getting tired, guys, so I'm going to stop this at the hour mark. I could do that, where I literally could go D16, store this, and then store this as A0.7. And I could store this. I could store it literally like this. And so the assembler would have to go grab D, if 16 bits, get D16A, just 1, do that, get that, and then that would store that number. And so if the effective address was, again, let's just say 32A1, if I wrote that, I would have to then go read this. So basically I'd make the add, so let's say we're going to go to add again. Byte. Add byte D1 32A1. Operand mode, source, destination. Destination would be the effective address. And then basically I needed something else to translate this into EA syntax. And then from there, I can then go grab EA object. I think that is what I'm going to have to do here. And then, from there, right? But that does get rid of information, so that could store basically a string as the source and the source and destination string format. And then from there, so this answers the first question. This answers number 1. This answers question number 1. How do we store the effective addresses in here? We have D6, stuff like that. This is for this one. I have to keep going to the other addressing modes and seeing what works and what doesn't. And then the question is, if the assembler finds this, let's go. Source is here. Maybe I'm doing what I supposed to be doing. So you have the source here, and we have the destination there, right? The source would go D1. The source, the sauce, the sauciest of sauces, the mother of God sauce, the best sauce in the world. What is the best sauce in the world to you? Does that probably, I guess, matters what you're reading, huh? Anyway, so if I'm So if I have this, right, back at this example. Let's go to add, shall we? I need to remember what page this is on so I don't have to keep doing this. Register op mode. I see. So we just have effective address is the mode and the register. The op mode and the register. So the op mode field would be this based on if it's a byte or long and how it's working. And then determine the addressing mode. This would go here. Oh, the 2 different questions. Oh my god, I get it now. Question 1 is the assembler. Question 2 is the emulator. Question 2 is the emulator. Because the emulator, how would that work actually? Because that would put in the mode 101 and the register number for AN. But how would the emulator know that I want to add 32 to that number? would it know that? How would the emulator, if I'm dealing with this, and I give it a 16-bit number, and I put in 101 for the mode, right? So we go up here, 101 for the mode, and the register is A1, whatever it is, right? How would the emulator know that I wanted to add 32 to it? Where is that 32 stored in here? Because it's a 16-bit number, so it's not obviously not in here. So where is it? Where is it? Where is it? How does the emulator know that? Because all it's getting is binary information. There's something I'm missing here. There's a piece I'm missing. So that's a really good question. If I have a 16-bit integer in there, how does the emulator know I need to add that 16-bit integer to the address? There is something I'm missing here. So I'm guessing that the line of the instruction would also include the integer I need. So it basically would be like, here's the bits for the instruction, and the next X many bits are the actual 16-bit integer. Monadic floating point on. Ooh, there's a monad in here. Okay. Okay, so I think there's something else I'm missing. There is something else I'm missing here. And it's really hot. It's really fucking hot. In case you didn't know that. I mean, it's not like there are the places that are more hotter than me, but this, I'm in the room that like always gets hot. And then I have the fan off, so you guys don't hear the fan running. But because the fan's off, I get hot. Alright. Because really, it would be basically like if I took this, I could basically do a 15 bits. So basically, bits 15 to 0. And then I would have the 16-bit numbers. Then I'd have bits 16 to 0, I think, of the number I want to put into that. And then if I need something else, I'd continue to add on it. I think that's how it works. I mean, because I can kind of do whatever I want to, but it has to work with an emulator. Of course, all emulators are different, and all assemblers are different. Oh my god. So, I mean, I might just start with that and just do it anyway. Yeah. Anyway, so guys, that is it for today. Lurkers, thank you for lurking. Watchers, thank you so very much for watching. What we got done today was we started to, after I realized that my bit rate was set way too high, I started to go into the address registers and ask questions like, how does this work? And how does this work? And how does this work? So next episode, we're going to attack this problem of assemblers and the emulators and how to add additional information to it to see if there's actually a specific way. Because, for example, if we have, this is the, add instruction. And then this is the, if this is D16, right? Is it like this? Or is it like this? Can you even see? I don't know. Or is it that? I don't know which way it is. And I don't know what other emulators are going to do. I mean, I can choose whatever I want to do myself because I'm the one making it. But anyway, so there we go, guys. That's it for today. Lurkers, thank you so much for lurking. Watchers, thank you all so very much for watching. And I will see you all next time.